Hello students, so far we have discussed about DC circuits, AC circuits and three-phase circuits, right? Now we are going to discuss about our third unit, that is electrical machines. Okay, in this unit we are going to deal with three types of machines mainly. First one is transformers, second one is induction machines, and third one is DC machine. Okay, now we are going to see about transformer. Okay, so first class is transformer introduction. Okay, so what is a transformer? So most of you have already seen a transformer in daily life. Okay, so it is one useful equipment in electrical power systems. Okay, so these are industrial applications of transformers. You can see the big size transformers. Okay, and we also have our domestic applications of transformers in household and electronic applications. Here you can see this is a transformer, and here this is a mobile charger. You can see a transformer in a mobile charger itself. Okay, and this is a computer motherboard, and this is a chip. So you can find a transformer in any electronic or household appliances. Okay, so like refrigerator, mobile charger, TV unit. Okay, so all these appliances are having a transformer basically. So why do we need to have a transformer in all these circuits? What is the function of this transformer? Let us proceed. So what is the need of a transformer? Generally, the electrical energy that is being generated at generating stations is in the order of 11 kilovolts or 33 kilovolts up to now. Okay, this is the voltage that is being generated at generating stations. Okay, but what is the voltage that a domestic supply get, that is 240 volts. Okay, so what is this 11 kV generating at generating stations, and what is this 240? So how it is being reduced from 11 kV to or 33 kV to 240? Okay, at generating stations it is 11 kV or 33 kV, but when it comes to our domestic supply it is around 240 volts. For line to line it is 400 volts, right? So how can you reduce this much of voltage to this 400 volts? Okay, so in most cases appliances are manufactured to work under some specific voltages. So here comes the transformers. Transformers are used to adjust the voltages to a proper level. Okay, transformers are used to adjust the voltages to a proper level. Okay, so many applications like TV, mobile. So mobile will be having a charger that will be charging the mobile with a voltage of 11 volts or 12 volts. So charger needs 12 volts, but our TV needs 240 volts AC supply. So every appliance has its own voltage specification, right? But how to transfer that voltage? The available voltage at our domestic supply is 240 volts. How can you transfer that 240 volts to 12 volts? Okay, so that is possible by using a transformer. Transformer transfers the energy, electrical energy, from one circuit to another circuit without changing frequency. Okay, so it can change the voltage from one range to another range, one level to another level, and it can change the current from one level to another level without changing power and frequency. So that is a transformer. Transformer is used to change the one level of voltage to another level. Okay, it can increase the voltage from one level to another level, and it can decrease the voltage from one level to other level. Okay, now let us see the basic components in transmission line are transformers. Okay, so here let us go back to generating station. Here we are producing the power at 11 kV or 33 kV. Okay, here this 33 kV will be increased, the voltage will be increased to 765 kilovolts. Here you can see. So why this happens is the more is the voltage in transmission lines, so V transmission, the less will be the losses in the transmission. Okay, that's why high voltage is transferred through the transmission lines. That's why this 765 kilovolts of voltage will be increased by the transformer from 33 kV. Okay, 33 kV will be increased to 765 kV right? That is possible by a transformer. Okay, so high voltage is economical to transfer the power from one location to another location. That's why voltage is increased from 33 to 765 kV. And next, but we need at our domestic supply we need 240 volts. So at this point, after the power is transmitted to a local substation, so substation will be having transformers. So mostly you have already seen substations. So they will be having a huge transformers which decrease the voltage from 33 kV to 11 kV or 11 kV to 240 volts like this, or 440 volts like this. So the substations mainly consist of transformers which are called step down transformers. That means they reduce the voltage from one level to another level. But at generating stations, the transformer which increased the voltage from 33 kV to 765 kV was a step up transformer. It step up means it is increases the voltage. Step down means it is decreases the voltage. Okay, so at substations we can see step down transformers. So this high voltage will be stepped down to a useful voltage, that is 240 or 400 at substations. So this is the useful work done by transformer. Okay, so now let us see the transformer. Transformer is a static device. So generally, as I discussed earlier, we are going to see induction machines and DC machines. So these two machines will be having a rotating part called rotor. It is a mechanically rotating part. So, but our transformer doesn't have any rotationary parts. That's why it is static. It is a static device. Okay. Now, transformer helps in transformation of electric power from one circuit to another circuit at the same frequency. Okay, frequency and power will be same. Even the voltage, current may vary. Okay, so what is the power here? Power is product of voltage and current. That means if from one circuit to another circuit, if voltage is increased, then current should decrease so that the product of voltage and current will be constant. So this is what happening in transformer. Okay, if voltage is increased from one circuit to another circuit using a transformer, the current will be reduced accordingly, so that the product of increased voltage and reduced current will make power equal to constant. Okay, the voltage can be raised or lowered in a circuit, but with a proportional increase or decrease in the current rating. So that is what P equal to V into I. P is same in two circuits. Okay, hence if voltage is increased, then current will decrease. So this is about power constant. So power is constant, frequency is also constant, but voltage and current ratings will change. So transformer is probably one of the most useful electrical device ever invented. It can change the magnitude of alternating voltage or current from one value to another. This useful property of transformer is mainly responsible for the widespread use of AC rather than DC. Okay, just because of transformers function, so AC is universally used. That means AC is mostly used rather than DC supply. Okay, because we have a facility to change the voltage level at any required point. Okay, we can change the voltage level from one value to another value using a transformer. Okay, that is possible in AC circuits only. So the input to the transformer is a AC supply. It is not a DC supply. Okay, electric power is generated, transmitted, and distributed in the form of alternating current only, not in DC. That means electrical energy generated in AC, transmitted in AC, and distributed in AC only because of transformer useful function. So transformers have no moving parts, as I told you earlier, no rotating parts, and they are rugged and durable in construction, thus requiring very little attention. They also have a very high efficiency, as high as 99%. So the only device in electrical engineering that has 90% of efficiency, more than 95% of efficiency, is a transformer. This is the highest efficient device in electrical machines. Okay, now let us see what is a transformer made of. Okay, so here transformer is having a two circuits first. Okay, so it is having two windings. So let us say this is coming from one line. Okay, so this is one line, and we are going to use transformer here to change the to change the voltage level. Okay, so here this is one line and this is another line. Okay, so here we are having different voltage here V1, and we need different voltage at this point V2. Okay, so how can you convert one voltage to another level? By connecting a transformer in between. Okay, so here I'm going to connect a transformer here. This is a transformer core. Okay, so this red color one is a transformer core. Okay, so this one. So it will be made of some CRGO steel material like this. We will see the entire discussion about transformer construction. Okay, so here this is a transformer. Let us say this is a transformer. Okay, here the winding will be having two windings. This is winding. Okay, here this is second winding. Okay, here you can see. So this is a transformer. So this is called core material, transformer core. And here the first winding is called primary winding. This winding is called primary winding. This winding is called secondary winding. This winding is called secondary winding. Okay, so here transformer is having two windings. First one is primary winding, second one is secondary winding. Okay, so on the primary, here you can see the statement. It essentially consists of two windings, the primary and the secondary winding, wound on a common laminated magnetic core. So this transformer core I explained is a magnetic core. It is common for both primary and secondary windings. Magnetic core. Okay, on a magnetic material we have wound two windings. One is primary winding and another is secondary winding. So the winding connected to AC source. So this V1 which is connected to AC source here. This is AC source. It can be single phase voltage. For single phase transformer it is single phase. For three phase transformer it is three phase. Okay, so there will be two types of transformers for single phase and three phase. Okay, so the winding connected to single phase AC source is called primary winding, and the one connected to load. So this one, this is secondary winding is connected to load. This is called load. Okay, the winding connected to load is called secondary. So first one is primary winding, which is connected to AC supply. So the winding connected to AC supply is called primary winding, and the winding connected to load is called secondary winding. Okay, so these are the two windings on a transformer. Now let us see the working principle of a transformer. How a transformer works here. Okay, so the basic principle on which the transformer works is Faraday's law of electromagnetic induction. This is called Faraday's law of electromagnetic induction, EMI. So this is the principle, or also famously called as mutual induction principle. Okay, so what is the principle of a transformer? That is mutual induction. So what is a mutual induction? So here we are having two coils, coil 1 and coil 2. That is winding is nothing but a coil, primary and secondary. So what is a mutual induction here? Mutual induction is nothing but here whenever a AC is supplied, AC current is supplied through a winding or a coil, so a flux will be induced around that coil. So I have already told you in an inductor what is happening in an inductor. When a current is flowing, there is a magnetic field produced around a inductor. I have already explained this. Okay, so this magnetic field is called self-inductance because of its own current. It is called self-inductance. Okay, but when this current in one coil producing a flux called phi 1, let us say this phi 1, this is producing a flux of phi 1. So due to current in first coil, a flux is produced by first coil, that is pi 1. When this pi 1 is linking with second coil, so when this pi 1 is linking with second coil, this is called mutual inductance. This is, let us say, pi 2 is produced in secondary due to the first coil. So this pi 2 1 is flux due to mutual induction. This is called mutual induction. Mutual induction. That means flux is produced in secondary coil due to the current flowing in the first coil. Okay, mutual induction is flux produced in second coil due to the current flowing in the first coil. Okay, this is called mutual inductance. Similarly, so when you observe the operating principle of transformer, so here I1 is the current supply current flowing through the first primary winding. This is primary winding, and there are number of turns. These are called primary turns are called N1. So this is a turn, right? This is one turn. This is second turn, third, fourth, fifth, so on. So these are number of turns. So N1 are the number of turns on primary, and N2 are the number of turns on secondary. Okay, so N1 is number of primary turn, and N2 are number of secondary turns. Okay, so due to the current in primary winding, there is a flux induced in the primary winding, and that flux is flowing through the core because the core is magnetic core. This magnetic core will allow the flux induced in the primary coil, and it will pass through the core and it will link with the secondary coil. Due to this interaction between flux due to first coil and secondary coils, okay, that means the flux due to first coil is flowing through the magnetic core and it is linking with the secondary turns. You can see here this flux is linking with the secondary turns which are wound on the same core material. So this flux will induce some current in the secondary coil. This is called Faraday's laws of electromagnetic induction. That means when there is a rate of change of flux, there will be a EMF production. That is electromagnetic induction principle. Faraday's electromagnetic induction principle. Actually, there are two laws according to Faraday. They are Faraday's first law of electromagnetic induction and Faraday's second law of electromagnetic induction. Okay, so I will just brief you about them. Okay, so first one is when there is a change of magnetic flux linked to a coil, it will induce an EMF across a coil. Okay, so let me write it somewhere. I'm taking blue pen here. So first law, I'm writing Faraday's first law. Change of magnetic flux linked to a coil. Change of magnetic linked to a coil induces an EMF. EM is nothing but voltage, right, across the coil. That means, so here let us take this is coil, right? So when the magnetic flux in this coil is changed, that means because we are supplying AC to the transformer, the AC will induce some time varying flux. That means it will be also AC, right? The flux due to AC current will be time varying, and the time varying flux links with the secondary turns will induce some EMF across this secondary voltage. That is called Faraday's first law of electromagnetic induction. Now let us see the second law of Faraday's electromagnetic induction, which is the EMF induced across the coil is equal to rate of change of flux linkage. EMF which was induced in the first law is equal to rate of change of flux linkage in the coil. Okay, so I will write down the equation here. So here this means the second equation is, say, what is the second equation saying mathematically is, so EMF induced in the coil is equal to rate of change of flux, that is d pi by dt, with a number of turns and having a negative. This negative sign indicates one special law that is called Lenz's law. This Lenz law is nothing but effect opposes the cause. Lenz law. Effect opposes the cause. Okay, so these are the laws here. Now let us find the turns ratio. So what is the turns ratio? We had a transformer and a primary winding, secondary winding, right? On transformer we have primary winding and secondary winding, primary turns and secondary turns. V1 supply voltage, I1 supply current, primary current, I2 secondary current, V2 secondary voltage, and E1, E2 are EMFs induced in primary and secondary. These are E1 and E2. Okay, so what is a turns ratio? Turns ratio is nothing but primary turns by secondary turns. Just ratio of turns. Primary turns by secondary turns. Primary terms by secondary terms. That is, primary turns are called N1, secondary turns are N2. Okay, now let us see. It is defined as the ratio of primary to secondary turns if N2 is greater than N1. That means if N2 is greater than secondary turns are greater than primary turns, the transformer is called step up transformer. This is very important. Okay, if number of turns on secondary are more than number of turns on primary, the transformer is called step up transformer. That means in this case the transformer will increase the voltage level from primary to secondary. Now in the second case, if N2 is less than N1, that means secondary turns are less than primary turns, the transformer is called step down transformer. Okay, in this case the transformer is going to decrease the voltage level from primary to secondary. These are two types of transformers, step up and step down. Okay, so at generating stations we are using step up transformers, and at substations we are using step down transformers. This is application of step up and step down transformer. Now let us see one important ratio, that is called transformation ratio. Symbol for transformation ratio is K, which is given as K equal to E2 by E1, EMFs on secondary to primary, and or V2 by V1, voltage on secondary or primary, I1 by I2, or N2 by N1. So this is, you can take any of this ratio to get transformation ratio. Transformation ratio K equal to E2 by E1, or V2 by V1, or I1 by I2, or N2 by N1. So using this transformation ratio, you can find voltage on one of the sides if other side is given, or current on primary or secondary if other side is given. Okay, the transformation ratio is defined as the ratio of secondary voltage to primary voltage. So this is the main definition actually. So it is denoted with K, as E2 is proportional to N2 and E1 is proportional to N1. This is can also be equal to N2 by N1. Okay, now let us do one simple problem so that you can understand all these things. Okay, so here a single phase transformer with transformation ratio as 1:2, okay, is supplied with a voltage. So this is turns ratio, not transformation ratio. The given question is right. This is turns ratio. Turns ratio as 1:2 is supplied with a voltage of 110 volts. Okay, the voltage supplied is 110 volts on the primary side. Find the voltage on secondary side. So we need to find the voltage on secondary side. Okay, let us draw a transformer. This is a transformer core. Okay, so let us draw windings on transformer. So this is winding, primary winding, this is secondary winding. Okay, so this is N1 are the turns on the primary, N2 are the turns on the secondary. So what is the given data? Given data is, so a single phase transformer with turns ratio, we given turns ratio. Turns ratio is nothing but N1 by N2, as we have seen earlier, that is 1/2. 1:2 is 1/2. Is supplied with a voltage of 110 volts, that is V1 is 110 volts AC supply. So V1 is 110 volts. Then we need to find where to be found is equal to secondary voltage V2. What is the value of V2? So how can you find this V2 here? Okay, how can you find this V2? So using your transformation ratio K, which equal to, which can be written as N2 V2 by V1, V2 by V1, or N2 by N1, or I1 by I2. Okay, so here we don't have K value, but we can find K value, right? K is nothing but N2 by N1. Here we have N1 by N2. So that is N2 is 2, N1 is 1. So K equal to 2. Okay, so we got K value. So K equal to V2 by V1. We have V1 value which equal to 110. So let us substitute that V1 and K values here so that we can get V2. V2 equal to K times V1. K is 2. V1 is 110. So it is 220 volts. So here secondary voltage is 220 volts. So you can simply say that this is 110 is on the primary and turns ratio is 1 is to 2. So this voltage will be doubled here. 110 volts will be on the second side, it will be 220 volts. That means this is a, what is that, this type of transformer? This is step up transformer. Okay, this is one simple example to understand these things. Okay, so in the next class we will be discussing more about this ideal and practical transformers. Okay, thank you.